Hi friends, this is Dr. Prafulla Dikshit and I'm back with yet another video on time series analysis. Now this is called time series analysis 2 from correlation to autocorrelation part 2. Now if you remember in the last video we said we'll discuss in the subsequent videos in more detail the transformation of correlation to autocorrelation. And also that we'll discuss the derivation of the formula of correlation and that of autocorrelation, that is from correlation to autocorrelation, the derivation of the mathematical, the applicable, so to say, the statistical formula for calculation purposes. However, I thought it would be a good idea first to discuss and develop kind of an intuitive, graphical, and a visual understanding of how this concept develops. So in the last video, if you remember, that was the part 1 of this video series of correlation to autocorrelation. We discussed the importance of the underlying concepts of time series analysis. We discussed the correlation concept, and we saw how we arrived at the conceptual formula of correlation, which is nothing but the ratio between the covariance of two variables with the standard deviations of the two variables. We also saw how this transformed into the autocorrelation formula by a simple replacement of the xy variables with xt and xt plus k, wherein xt is a time series variable and xt plus k is a lagged value series of xt. We then discussed the difference between correlation and covariance, and most importantly that correlation is nothing but a standardized covariance. Further, we discussed about the autocorrelation concept as derived from correlation, and that we'll discuss this in further detail in the subsequent videos. Now in this video, that is part 2 of correlation to autocorrelation, we'll try and understand how correlation transforms to autocorrelation in a graphical and intuitive way, as we talked about it just now. Specifically, we'll see how in graphical terms correlation transforms to autocorrelation, and we'll try and get a feel of what correlation between two variables x and y looks like. We'll try and see how this correlation between x and y transforms to correlation between xt and xt plus k, which are two time series variables, and it transforms into an autocorrelation of xt, which is a time series variable. Finally, we'll see how autocorrelation exists between the lagged values of xt. Okay, so what we have here is the Apple computers, or AAPL, closing one-day data for around 1 year period, and it starts from say 30/7/2012 and goes all the way to 29th of November 2013, and we have the 7-day lagged values of the same series, and then we have the 14-day lagged values of the same series. Now let me show you what I mean by this. So basically the AAPL daily time series can be represented by xt, okay, and the subsequent lagged value series can be represented by xt plus k, okay, and let's see if we substitute the values of k into these expressions. What we get is the first one, we get xt, okay, and then we get xt plus 7, and then we get xt plus 14, and that is what I'm talking about right there. So next what we did was we plotted the graphs for these three series, that is the original series and the 7-day lagged and the 14-day lagged series. Okay, so we have the line graphs of the three series, the AAPL closed series, the 7-day lagged series, and the 14-day lagged series. And as you can see right here, this particular series is it is uh, varying quite a bit, as you can see here. This is varying quite a bit. There's a lot of volatility in this particular series, although the other two series are also for the same period. What you'll see is, right here, let's see this one. Uh, this series right here, this is also varying, but the variability is less, as you can see right here. Okay, but they are following a similar pattern, as you can see. There is similarity, but there is also a difference in terms of the volatility. What do we have here? Over here, as we can see, uh, there is again similarity, but there are broader patterns, and the volatility or the disturbances or the ups and downs are still lesser in this particular case. So we see that there is similarity between these three series, but there is also a difference between them in terms of the volatility. So more importantly, if we compare these series subsequently, either the AAPL close series with the 7-day lag series and then with the 14-day lag series, we can see right here that there is talking about the similarity between two subsequent series. The similarity between the lag 0 series and the lag 7-day series is greater than that between, say, lag 0 series and the lag 14-day series. Or conversely, we can say if we compare the similarity between the 7-day lag series and the 14-day lag series, which is the next lag series, the similarity is greater than what is there between the 0 lag series and the 14-day lag series. So what this means is that as the lags increase, so the similarity between the original series and the subsequent lagged series decreases. Okay, or conversely, we can say that as the lags decrease, the similarity increases. Now, this has connotations for correlation and covariance. Now, what this points to is the presence of a correlation in terms of the similarity, the correlation and covariance between two subsequent series, that is the original series and the lagged series, and that this similarity or the correlation or covariance decreases as we move ahead in the lag time span. That is, as the lag increases, the correlation or covariance decreases in general. Okay, there can be exceptions to this rule, but in general, overall, the correlation or the covariance decreases as we move ahead from lag 0 to say lag 7 or say lag 14. So right here we have kind of a graphical evidence of uh, the correlation or covariance between two subsequent uh, lagged time series uh, variables. That is, if we see from lag 0 to lag 7 and lag 7 to lag 14, the similarity between the subsequent values or variables, these series, denotes covariance or correlation between these series. Now, why I'm using covariance and correlation interchangeably? Because as you remember from the last video, correlation is nothing but the standardized covariance. So as you remember from last video, correlation of xt with xt plus k is equal to the covariance of xt and xt plus k divided by the standard deviations of xt and xt plus k. And this is what proves that correlation is nothing but standardized covariance. And it is standardized by the standard deviations of the two variables. This in turn came from the correlation formula, which was the correlation between x and y is the ratio of the covariance between x and y and the standard deviations of x and y. So what this standardization means in graphical terms is that when we talk about a correlation is equal to the covariance of two variables. Let's say these are the two variables, these are two subsequent lagged variables. Um, there is a covariance, that is the way these two variables vary, So covariance means the similarity in the way they vary. So there is a variation right here, there is a variation right here, and there is a similarity in the way they are varying, and which is evident from the similarity in the graphical pattern. Okay, and the way this covariance is standardized is through the standard deviations. The standard deviation is a measure of the variability in the given variable. So basically, we divide it by the variability in this particular variable and the variability in this particular variable. So correlation gives us the ratio of the covariance, that is the similarity in the variability of these two variables together, and the individual variability in the two variables as a ratio of the similarity in variability of the two variables to that of the variability or the product of the variability in the two variables. Now, since these are lagged values of same variable, or these are the lag values of a time series variable, the correlation we are referring to here is not about two different variables, the same variable and its lagged values. In fact, it is about the same variable. So we'll just replace the word correlation with autocorrelation. So we can say if, and as we have seen in graphical terms, we can say correlation is the ratio of the covariance to the variance of two variables, say x and y, versus autocorrelation is the ratio of the autocovariance to the autovariance of two variables, say xt and xt plus k. So that's interesting, and these two comparative statements and comparable statements right here, and the graphical demonstration from which they emanate, which we just saw. I have to say, based on that, I have to say that this has given us the basis for the conceptual transformation of correlation to autocorrelation. And this is really, really interesting, and I want to highlight this. Let me just highlight this for you. This is really important and seminal. Okay, now that's about it for this video. In the subsequent videos, we'll discuss the exact derivation of the formula of autocorrelation from correlation. If you really like this video, do give it a thumbs up. If you think it can be useful for others, do share it. And do not forget to subscribe it if you would like access to more such videos. Don't forget to press the bell icon. Till the next video, goodbye, take care, and thanks for watching.